Hello, and welcome to this introductory video on the electric potential and potential difference. We introduced the idea of an electric potential energy in an earlier video, and we concluded that the electric potential energy was just the negative of the work done by the electric field or by the electric force. If you have a constant electric field, then basically the work is something like Q times E times D. And in fact, even if the electric field isn't quite constant, at some little bit of motion, it's roughly constant, so some little bit contributes something like this, and then electric field might be varying as a function of position, but it is certainly true that the test charge, Q, will appear in our expression. So if it appears in our expression, then this is a lot like what we did with the electric field, and realize that, well, there's an energy, which is the interaction of the two charges, of the test charge with my original charge, but I can see from this that I could divide out that test charge. Because the potential energy here is basically ending up proportional to Q, I can go ahead and divide it out. And when I divide it out, I get exactly this thing, which we're going to call electric potential. And we'll represent it with a symbol V, and we'll use units of volts to describe this thing. So potential energy, being a potential energy, would have had units of joules. A joule per coulomb is a volt. Now, the really fundamentally important thing in any discussion that we've had involving a potential energy has not actually been the value of the potential energy, but rather of the difference. And it's just like that here. It's not so much the electric potential energy that matters, but the difference in electric potential energy between 2 points, which will govern whether our electron or whatever charge we're moving has sped up or slowed down as a result of moving along that path. And so if we're now taking a potential instead of a electric potential energy, that's just the potential energy divided by the charge. So fundamentally, the thing that's going to matter here, again, is the electric potential difference. So this potential difference, delta V, is going to determine whether things are speeding up or slowing down or what they're doing, or whether they even move in the first place. So our potential was just the potential energy divided by Q. So not surprisingly, the change in potential, or the potential difference, is the change in potential energy divided by Q. Okay, which of course means that if we ever wanted to convert this back into discussing things about how the electron or whatever charge that's moving might speed up or slow down, we would need to put that back in terms of actual energy. So then we can write that the change in potential energy is just Q times delta V. It's just the test charge times this potential difference. Which is great, because now if we're specified some potential difference, and I ask you, suppose that you drop an electron there at some position, and it's got this potential, and then it moves across and ends up at this potential, then just by looking at that change in potential, you can tell me what the change in its potential energy was, and then applying energy conservation, you can tell me what the change in its velocity was, for instance. All right. So that is how these things are all interrelated and enable us to solve some problems. We label the potentials in terms of their volts at different locations, and we can figure out what happens then to the potential energy of some test charge that moves between those locations.